Okay, today we're going to be looking at eigenvalues and eigenvectors. We're going to start off with a visual example, and then we're going to look at the maths behind that example, and then hopefully be able to combine those two things together. So what we're looking at here is a two-dimensional space with basis vectors I and j, and we want to perform some sort of transformation to this space. So let's say our transformation is going to look like this. Comes up. So if we've done a transformation here, we've done some sort of stretch, kind of along this diagonal direction. And if we look at that underlaid axes from before, we can see that our new I basis vector is now pointing at position 2, 1. As we can see, it's got coordinates 2, 1 there. And our j vector has got coordinates 1, 2. So what do we think this transformation is? How do we express this transformation, I should say? So let's move this up to here. And what we're looking at now is some matrix A, which describes the transformation that we've just done here. So we can actually get this transformation from the new basis vector coordinates. So we can say that I, which is at 2, 1, gives us the first column of A. So we just write 2, 1 in there. And then for the second column, we've got J. So that's 1, 2. And this obviously works backwards as well. If you're given a transformation matrix, you can work out where those new unit vectors are going to be. So what we want to find now, if they exist, is any vector which would be unchanged in direction after this transformation. So it's going to be different for every transformation matrix. We've done some sort of stretch along this direction. And we want to know if there's any vectors that would be potentially scaled, but not changing in direction. So you might guess, because we seem to have done some sort of stretch along this direction, that if we had a vector that was conveniently pointing roughly in that direction, then perhaps that vector would still be pointing in this direction, but just be stretched. So this might be one of the eigenvectors, there might be another one, and we're going to look at the maths to try and find out. So let's start by our definition of an eigenvector. So we're looking for some vector v that when we multiply it by a, we end up with just a scaled version of that v. Now, we're going to solve for, first of all, the eigenvalue, which is this lambda here, and then we're going to use that value to solve for the eigenvector v, which is here. So, first thing we need to do is introduce the identity matrix onto this right-hand side, and all this is doing is just turning it into a matrix vector product instead of a kind of scalar vector product, which we need to be able to kind of manipulate this equation. So first thing we're going to do now is shift this all to the left-hand side. So we're going to have AV minus lambda I V, and that's going to equal the 0 vector, which is just a kind of, in this situation, we're going to have a column vector of 2 zeros. Now we can factor out the V, so we end up with A minus lambda I, all multiplying v, once again giving us the 0 vector. Now, assuming that v is not all zeros, which wouldn't be a very useful solution, we can actually work out that this augmented matrix here is going to have a determinant of 0. So this augmented matrix has to have a determinant of 0, and that is because there's no other way of multiplying a matrix and a vector together and getting a 0, assuming this is non-zero. So with this information in mind, this is going to be very useful. We're going to be able to solve for our eigenvalue now. So let's rewrite out our augmented matrix A minus lambda I. That's going to look like this. So we're going to have 2 minus lambda, 1, 1, and then 2 minus lambda. And those lambdas on the diagonal are again because of this identity matrix that we've used to multiply it. So how do we work out the determinant of this? So we know the determinant is going to equal 0, and that's going to be how we work this out. So the determinant is going to be 2 minus lambda times 2 minus lambda, so that's the first diagonals multiplied together, and then we do minus the other diagonal there, and that's going to just be 1. And we know this equals 0. So let's expand this out and simplify it. We've got 4 minus 2 lambda minus another 2 lambda plus lambda squared minus 1. And simplifying this gives us lambda squared minus 4 lambda plus 3. Lovely. So if we factorize this and then solve for lambda, that will give us our solutions. So we've got lambda in both brackets. We need two negatives to get this negative when they sum together, and then two negatives will give us a product positively. So we get -3 and -1, hopefully. So now all we have to do is work out what lambda would have to be for this to be the case, and that's going to give us lambda 1 equals 3, and then we'll say lambda 2 equals 1. Lovely. So let's get rid of this for now, and what we're going to do is now substitute in our values of lambda, and we're going to see if we can solve for our eigenvectors. So let's do lambda equals 3 first of all. So there we go. So what this looks like in this case is going to be 2 minus 3. So we're going to have a matrix of -1, 1, 1, and then -1 again. Now, if we multiply this with some vector, we'll call this vector 1, 1 and vector 1, 2. So these are the components of our first eigenvector that we're kind of looking for here. And what we're doing here is we're saying if we multiply this matrix, the augmented matrix, with some eigenvector, which is looking a lot like this expression here, we know that's going to give us the 0 vector. So we know this is going to give us a vector of zeros. Now we can just look at the top row for now. We'll say we've got -1 times v1, and that's going to be plus to 1 times, so that's v11, plus 1 times v12, which is the second kind of element of our first eigenvector, and we know that equals 0. So looking at these, we can quite easily see there's going to be an infinite set of solutions, but we actually don't mind what solution we choose. So we'll just choose the simplest one. We could say if this was 1 and this was 1, then we'd end up with -1 plus 1, which gives us indeed 0. So our first eigenvector is going to be so our first eigenvector is going to be 1, 1. And we can actually see that is exactly what we were looking for here. So we have this original eigenvector 1, 1, and we can see that that is being stretched along that direction, but we now know that it is definitely maintaining its same direction. And then the question is, what has it been scaled by? What is that scale factor? And that is given to us by lambda. So our eigenvalue tells us that this eigenvector has been scaled by 3 times. And of course, we could have chosen any values for this. We could have said this was 5 and 5, and that would have given us -5 plus -5, still gives us a solution. And if we had that going along here, that would then be stretched to kind of 15 in this direction. So quite often this is turned into a unit vector, just for convenience, but for now we'll just have a look at something that's going to give us an idea of how this looks. So let's get rid of this scenario, and we'll try this out with with lambda equals 1. So this is supposedly going to give us a second eigenvector. So if we have lambda equals 1, then we substitute that in here, we're going to end up with a matrix of 2 minus 1, which is 1, 1 again, 1 again, and then 2 minus 1, 1 again. And once more, this is multiplying, I should say v2, 1, and v2, 2. And again, that's going to give us the 0 vector. So now we're looking for this v2 here. And again, the same thing applies. We can just do the top row multiplication, and we end up with 1 times v1 plus 1 times v2. And once again, this has got an infinite set of solutions, but we can actually just find any set that will, any pair that will solve this. In this situation, we could have v equals -1, so this would give us -1, well, 1 times -1, and this would give us, if we had v equals 1 here, so we have 1 times 1, and that's going to give us, again, 0. So our second eigenvector is now -1 and 1. So what does that look like on our original axes? Well, we're going to have -1, 1 pointing perpendicular to our original point. Sorry, our original eigenvector. So it's pointing out perpendicularly to our original eigenvector. And how is our eigenvector going to be scaled? Well, it tells us that it's going to be scaled by just a factor of 1. So actually, as we can see on the new grid, this point here is still in line with the original position of -1, 1. So our new scaled eigenvector is actually just kept as its own scale. So what we're seeing here is that our two eigenvectors to describe this are pointing along 1, 1 and minus 1, 1. My closing questions would be, is there going to be a transformation that would have no eigenvectors? And for that, I would urge you to consider potentially a rotation that would kind of move these basis vectors kind of around in this direction. And in this situation, we would have no eigenvectors. And then your homework is, could you tell me one that would have just one eigenvector in 2 dimensions? And could you tell me one that would have infinite eigenvectors in just 2 dimensions? Okay, thank you very much.